So our next speaker is Daniel Agterberg from the University of Wisconsin. And he's going to talk about Hubbard models for non-relativistic spin splitting.
Okay. Okay. Yeah, well, thank you for the invitation. I also want to thank the organizers for arranging this workshop, since it helps important international collaborations such as this thrive in these difficult times. All right, so I'm going to talk about Hubbard models for non-relativistic spin splitting. And what I mean by spin splitting is the energy between up and down fermions in momentum space. And what I mean by non-relativistic is simply that these spin splittings exist without spin orbit coupling, but come from exchange interactions in our materials. Okay, so let me, before going into the talk, highlight my collaborators, and in particular, the two people that have done the research. So the work I'll be talking about in the context of altermagnetism, that was done by Merce Roeg, who is a postdoc here. And I'm also going to talk about odd parity spin splittings, and that is work done by UAU, who is also a postdoc here. All right, so what do I mean by spin splittings, and where do spin degeneracies come from? So throughout this talk, I'm going to assume that the non-magnetic states have both time reversal and inversion symmetries. And both these symmetries take a momentum k to momentum minus k. Time reversal flips spin, inversion does not. When we have both these symmetries, this means that we have the product of the two, and that's a symmetry that takes momentum k to itself. Now, since we're talking about fermions, this symmetry squares to -1, since time reversal squares to -1. And this is a symmetry at each momentum point k in the Brillouin zone. And so this guarantees that we have a twofold spin-like degeneracy at every point in momentum space. So to get a spin splitting, we need to break this TI symmetry. We can do that in two ways. The first way is to break time reversal symmetry and preserve inversion symmetry, and that'll give altermagnetism. And I think you've seen a few examples of that already in this talk. And so here in altermagnetism, sigma z denotes my spin matrices. And so this tells us that spin up and spin down have different band structures and different Fermi surfaces. And so here is a picture of a D-wave altermagnet, which satisfies the fact that this is inversion symmetric. The other way we can get a spin splitting is to break inversion symmetry and preserve time reversal. This gives us odd parity magnetism, and we're all familiar with a common example of that, and that is a Rashba spin orbit coupling. And so here, the spin splitting is odd under momentum k goes to minus k. And then you can see that in this picture here, where in this direction we have spin up, but in a minus k, we have spin down. So I'm going to talk about both of these. I may not get as much time as I want to talk about the odd parity magnetism, but I'll tell you some of our newer results in altermagnetism. Okay, so one of the key ingredients in this talk is non-relativistic spin splitting. And you have heard about this at this conference, but the key there is that we can rotate spin and spatial operations separately. And so this allows us to introduce the notion of spin space groups, which have been very heavily discussed in the last couple of years. And a common example is a twofold rotation in spin space, which flips the spin, and say a fourfold rotation in real space, which gives, a structural fourfold rotation. Now, when we have this no spin splitting, we can get, when we have this no spin orbit coupling, we can get large spin splittings. And you've heard about that in collinear antiphonetics-like systems, which are altermagnets. And it also can occur in non-collinear states, which you've also heard about earlier today. And one common example of that is P-wave magnets, where you get this non-collinear structure where you see the spins on the cerium sites in this particular example are 90 degrees rotated from each other, And this gives rise to a spin structure momentum space that is odd under k goes to minus k. And so there have been a few papers already discussing that. This morning, you heard a talk about the experimental observation of this. And then some of the work we're talking about will discuss this as well. In the context of these spin space groups, only very recently has a complete classification been done of every possible type of magnetic state you can get within these spin space groups. And it turns out there's a great number of them. Not all of these have spin splittings, but many of them do. And so our goal was to kind of develop minimal Hubbard-like models to derive such spin splittings. Now, before we came into this, we did a search to see what kind of minimal models already exist for non-relativistic spin splittings. And in fact, it turns out back in 2007, some models had been developed. And these models are all single band theories. And the idea is that you have a doubly degenerate spin up and spin down Fermi surface. And that spontaneously deforms separate deformations for the spin up and spin down Fermi surfaces, where the spin down develops, say, this shape and the spin up develops this shape. And you get naturally this D-wave alter-magnet state that I showed you earlier. And a common example, this is known as a Pomeranchuk instability, and a common example of that is a Stoner instability. So these kind of theories, these single band theories, give you spin splittings of the type we're interested in. And in fact, you can also do it for p-wave magnetic states. So you can do it in the odd parity and in the even parity channel. But I have a critique of these models in the context of altermagnets as we know them today. So in particular, in these models, the spin splitting is actually the primary order parameter. But I think, as many of us are aware, we understand now that altermagnetism comes from an anti-ferromagnetic state that exists in some sublattice of our system. And the spin splitting then becomes a secondary order parameter. And so, in fact, generically, if we want to describe altermagnetism in the context we understand it today, we have to go beyond single band theories because we're going to have more than one degree of freedom in our unit cell. All right, so let me turn to what we have done in this context. And then also let me give you a flavor of the kind of Hubbard models we're working on. And to do that, I'm first going to talk about altermagnetism, and then later we'll get to the odd parity magnetism. But as I mentioned early on, not as I mentioned early on, but altermagnetism, as you've heard today, preserves translation symmetry. And so its order parameter, which we call here J, can be characterized by a representation of the point group. And I think you heard about that this morning. And so its order parameter has a spin part, which is just a spin vector, but then also has a spatial symmetry gamma n. And in the models we have today, we're going to be worried about the point group symmetries and then the spatial symmetry or the irreducible representation to which the altermagnetism belongs. And just to understand how sublattice plays an important role in this, I'm going to consider a simple example of just a simple square lattice in 2 dimensions. And so here is the square lattice, but we're going to start with having one atom per unit cell. So in this picture then, I've chosen a particular Vyckoff position of this space group. This Vyckoff position is the 1A site. It has the full tetragonal symmetry of the square lattice. And now I'm going to impose magnetic order on this, but that magnetic order has to preserve translation symmetry. And in fact, there's only one possibility. That possibility is ferromagnetism. And that ferromagnetism is unchanged under all spatial rotations. And so this irreducible representation of the point group is the identity, the A1G irreducible representation. And that's the only possibility we have here. And we can examine the consequence of this state on spin splitting in momentum space. And because we have full point group rotational symmetry, that tells us that to first approximation, this spin splitting is going to be the same everywhere in momentum space as drawn here. Okay, so how do we get altermagnetism? Well, the solution is then to consider the sublattice degree of freedom. And here I'm considering a Wyckoff position where there's 2 atoms per unit cell. And this is the 2f Wyckoff position in here. And now I can go through the same argument. I can ask, how can we make magnetic states that preserve translation symmetry? And of course, we can do the ferromagnet as above. But now there's clearly a second possibility, and that's just making an anti-ferromagnet on this sublattice degree of freedom. And then we can see that this anti-ferromagnet is unchanged by a spin flip, red to blue, followed by a 4-fold rotation in real space. That switches both these sublattice degrees of freedom. And from this, we can deduce the structure of the spin splitting in momentum space. And so in particular here, I've shown some spin splitting along the kx direction in momentum space. So this is, say, the upspin, and this is the downspin. But using this symmetry, I know that if I do a 4-fold spatial rotation, which takes me from kx to ky, I have to flip the spins. And so I have to go from up to down and from down to up. And this tells us generically we get these zeros in the spin splittings, but it also tells us that here, this anti-ferromagnetism is the primary order, and the spin splitting is a secondary order parameter. All right, so that's enough information to understand the kind of Hubbard models we're looking at. And so here, what I'm doing is just summarizing these Hubbard models. And these are sublattice Hubbard models. And what we did is we identified all space groups with Wyckoff positions of multiplicity 2. So we have a 2-atom sublattice, like the second example I showed you. We required all our Wyckoff site symmetries to contain inversion symmetry. This allows us to get altermagnetic spin splittings. We can generalize this later when we talk about the odd parity spin splittings. And then the models we examine contain on-site Hubbard interactions on each sublattice site, and then all tight binding terms allowed by symmetry. And then typically we imagine a single orbital is electronically relevant on each site. Okay, so we can study these models within RPA, which is what we did. And then we can find that you can stabilize altermagnetic states. I'm not going to really discuss that in much detail here, but the key thing to remember is that when we carry out this process, we can get 40 space group Wyckoff symmetry pairs. And amongst all these models, we have a variety of all possible point groups that we're interested in. And in addition, we can get D wave, G wave, and I wave altermagnets. So we've spent some time studying these kinds of models. And so what I want to talk about today is a couple of the more recent results, and those are the ones highlighted in blue. In particular, if you look at DFT results, you can often see that the anomalous Hall effect is observed to be large in DFT, but the magnetization, when it exists, is very small, are sometimes small and sometimes large. So we're going to address that first. And then I'm going to turn to how we can generalize these sublattice Hubbard models to non-relativistic odd parity spin splittings. All right, and then we have a series of other results, but I refer you to some of our papers to look at that. And there's also some related papers in the literature that discuss models of a similar nature to those that we discussed here. Okay, so let's turn to the first problem. And that is the role of spin-orbit coupling on these altermagnetic states and the interplay of the anomalous Hall effect, spin ferromagnetism, and quasi-symmetry in these. And I'll tell you what quasi-symmetry is in a second. All right, so we know that if we want to get an anomalous Hall effect in an altermagnetic state, and if we want to get a spin ferromagnetic moment in these altermagnetic states, we have to turn on spin orbit. We also know that the anomalous Hall effect and ferromagnetism share the same symmetry, so naively we expect them to have the same largeness. So if the anomalous Hall effect is linear in spin-orbit coupling, we expect the ferromagnetism also to be linear in a spin-orbit coupling. And if you look at the DFT literature, you find that this is in fact not the case. So in particular, you generically find the anomalous Hall effect is large, so it is linear in spin-orbit coupling. And that's already been pointed out by Libor and co-workers a few years back, and more recently by Igor Mazin in the context of ruthenium dioxide and in this iron Sb2. But in particular, these are both altermagnets that have this dxy-like symmetry. This material is tetragonal and this material is orthorhombic. And if you look at the anomalous Hall effect, you find that it scales linearly in the spin orbit. So this is spin orbit, and you can see there's a linear slope here. This is anomalous Hall effect. And so we call this large in both these cases here. However, if you go further and you look at the magnetization that's also generated by the spin orbit, you find that these two materials are dramatically different. The magnetization in the case of the ruthenium dioxide is incredibly small. So our calculations show to be on the order of 10 to the minus 7 Bohr magnetons. And in the context of FeSB2, it's much larger. It's 5 orders of magnitude larger, on the order of 10 to the minus 2 to 10 to the minus 1 Bohr magnetons. And you can also see that the scaling with spin orbit coupling is very different. So here it's quadratic with spin orbit coupling, and here it's linear with spin orbit coupling. And so what we wanted to do was to try to understand the origin of this difference by examining these sublattice Hubbard models that I mentioned. All right, so that's what we did. And the first result we can get right away, which agrees with all the DFT calculations, is that the anomalous Hall effect is always linear in the spin orbit coupling. And so it's always, in that sense, a large effect. And then we turn to calculating the size of the ferromagnetic spin moments that come out. And the way we did that is we can use our models to calculate free energies for our altermagnets. And then in these free energies, we can bilinearly couple the ferromagnetic moment and the altermagnetic order parameter. And so the ferromagnetism here is denoted by M, and the altermagnetism is denoted by J. And here is an example for example in ruthenium dioxide, where we have this D4H point group and we have this XY altermagnet. This invariant is allowed by symmetry. So we can calculate with that within our theories. And then we find that the coefficient in front of that is sometimes linear in spin orbit, but sometimes it vanishes to linear order in spin orbit. And in fact, when we go through all the possible point groups and all the possible altermagnetic symmetries, we can find out when it's linear in spin orbit and when it vanishes. So for this point group and this particular altermagnetic symmetry, here we have a linear in spin orbit term, but where there's an X, it vanishes. And this, when it's linear in spin orbit, we get a magnetization that's linear, but when there's an X, we get a magnetization that's higher power in spin orbit and therefore small. So we can compare our model results to DFT, and we find we get good agreement with DFT. So in particular, if we look at some examples like this C2H point group with some D-wave altermagnet, then here in this DFT paper, they calculate the spin moment versus the size of the spin orbit, and they find it varies linearly and it's very large, something on the order of 0.2 Bohr magnetons. And we can also look at other examples. We can look at FeSB2, studied by Igor Mazin and co-workers, and there they find that the spin magnetization is vanishing, but the anomalous Hall effect is large. And we can go back to this classic paper from 2020 on ruthenium dioxide, where they show the anomalous Hall effect is large, but if you look closely at their paper, you can also see that the spin ferromagnetic moment is vanishing. And so what we find is that also this is true in MNT. So what we find generically is that our model results reproduce all the DFT results. And so this suggests to us that there must be some deeper reason for why this happens, because the DFT results, of course, contain many more bands than our two-band model results. All right, and so we thought about this, and we realized the explanation is buried in a notion that we borrowed from another context called quasi-symmetries. And so let me explain what I mean by quasi-symmetries and how it can explain why sometimes we get small moments and why sometimes we get large moments. So when we talk about altermagnets, we talk about this sort of in the standard limit when there's no spin orbit coupling, and we characterize all the states by a spin space group. But then we also have the usual limit, where in large spin orbit coupling, we have magnetic space groups. And in magnetic space groups, the spin and the spatial rotations are tied together. The context of quasi-symmetries refers to symmetries in between these. So we don't have the full symmetry of the spin space group, but we have larger symmetry than the magnetic space group. And in the particular context we're concerned with is when we turn on the spin orbit coupling in only one direction. So here, as an example, we've turned on the spin orbit coupling along the z direction. Then the Hamiltonians generically have full spin rotational symmetry around the z-axis, but not the full spin space group. And then we can ask the question, do we have this bilinear coupling invariant in the presence of only this single component of spin orbit coupling? And so as a particular example, to show you how this works in some more detail, we can consider, again, this altermagnet with dxy symmetry in the tetragonal group D4H, where this invariant is allowed by symmetry. And we can now impose that we have this rotation around the fourfold z-axis in spin space for this. And under that rotation, mx to my goes to my minus mx. And so under this rotation, we see that this invariant picks up a minus sign. So under this quasi-symmetry, this is no longer an invariant and consequently must vanish. We can do the same thing for choosing the spins along x or the spin orbit coupling along y. And we find that this invariant vanishes for all three directions. And it explains to us then why this term, this magnetization, cannot appear in this model. And if you do a detailed analysis, you find that this gives an understanding of all the DFT results. And so we have a sort of, I think, a deeper understanding between the interplay of ferromagnetism and spin orbit coupling in these altermagnets. All right, so I see I have a few minutes left. And so now let me switch gears to odd parity spin splitting. And in particular, when we were doing our RPA analysis of our Hubbard models, when we found that the instability lied in the Q equals 0 channel, then we knew that we could have an altermagnet. But of course, depending on our tight binding Hamiltonians, we could also find instabilities, say, at Q equals pi 0. And so we began to ask the question, what does sublattice do to magnetic states when we have an instability at Q equals pi 0? And so the first thing we did is we constructed Ginzburg-Landau free energies to understand this. And so here, let me just set up the framework for this. So in particular, we're examining situations where you have two spins on two sublattice sites in a unit cell, but now these sublattice sites are related by inversion between them, and we antiferrometallically order these along the x direction. So we're going to assume spin rotational and inversion symmetry, and then for the system, we're going to write down a Ginzburg-Landau free energy. And I'm just going to tell you that we have actually imposed additional symmetries here that I'll explain. So there are terms in this free energy that are allowed by spin rotational and inversion symmetry, but just listen along as I explain the sort of general analysis here. All right, so this is our free energy. We have a quadratic term, and then we have 3/4 order terms. And it's not hard to write down the ground states that are allowed within this Ginzburg-Landau state free energy. We find three particular ground states as shown here. In one case, we have spin ordering on one site and no spin on the other. The other case, spin orders on both sites and they're parallel. And in the case that we're interested in here, we get this coplanar state where on one side spin points, say, along y, on the other side it points along x. We can then further study these states and we can realize that they all have a special feature. They all have a translational invariant symmetry breaking that was not present in the non-magnetic states. And so to see in this particular state, we have an order parameter which was S1 squared minus S2 squared. This is a spin scalar order parameter, but because inversion is between the states, this breaks inversion symmetry. So it's an odd parity kind of piezoelectric state. In this state, we have this S1.S2 order parameter. And it turns out this is nematic order. And this kind of order is well known in the context of iron-based materials. And so, in fact, it is the nematic order often discussed in that context. And then, of course, we have this S1 cross S2, which is non-zero in this state. And this state is a spin, this order parameter is a spin vector, but it is also odd parity. So I'm going to skip this explanation of this symmetry here and just talk about the consequence of this particular last state. S1 cross S2 is time reversal invariant. So if I flip the two spins, it doesn't change sign. It's odd parity. And so that means in our Hamiltonian, we're permitted to have, in our microscopic Hamiltonian, we're permitted to have some spin vector times some function f of k. And because of the odd parity, this function f of k must be odd under k goes to minus k.
Daniel, you have 2 minutes.
2 minutes. Okay, let me then, this was the main point I wanted to say. This generates our odd parity spin splittings, and here's an example of that again. And then I'll just point out that we can find many examples of where this is valid and where this works. So 421 theories. We can get P wave, S wave, H wave splittings. We can characterize what space groups this occurs in. And the key point that you need to know is that you need to have a non-symmorphic space group for this to work. But then we can also compare to DFT results and show that the spin splittings are large. And then I'll just skip right along to my conclusions and then just leave it here and then give you some time to ask questions. So I'll stop there. Thank you.
Thank you. Yes, we are a bit tight, so Jerome.
Thank you, Daniel, for a very nice talk. I was wondering about the quasi-symmetries that you introduced. So by switching on just one spin orbit coupling, say, right?
Yeah.
My question would be, are these symmetries only present in models, or are there real materials that would have such quasi-symmetries?
So the reason we invoke so no real materials will have these quasi-symmetries, but what we can answer, let me see if I can go back to my slides to show. Okay, let me explain. So what we're interested in is, does the ferromagnetism appear to linear order in spin orbit or not? And what we can show is that the quasi-symmetries tells us that to linear order in spin orbit, there is no ferromagnetism, and it must appear in higher powers in spin orbit. And so these quasi-symmetries are simply when we include spin orbit along one direction only. And I think there is no real material that has it, but as a conceptual tool, it's very useful to understand what effects show up to linear order in spin orbit and what effects show up to higher order in spin orbit. So I hope that answers your question.
It does. Thank you.
Sasha?
Yeah, okay. Actually, still there is a question. It reminds me the difference, let's say, between classical charge density wave and excitonic insulator. So I just wanted to ask, is a similar thing like Pomerantuk-like instability could be a reason for formation of the orbital ordering, or another way, the orbital ordering by exchange of phonons or something could be just go the first. Is such a division or no?
So, so I don't know the specific answer, but certainly, so I think charge density waves are typically not discussed within the context of Pomeranchuk instabilities, but you can talk about nesting, which means that they can be described by some sort of single band theory. So there is a generalization to single band theories. And certainly, okay, I haven't checked in detail, but I can imagine that you can discuss the energetics of multi-band versus single band cases in this case and see if there is some direct analogy like you suggest. I don't know the details there, and we've done a little bit of that in the context of these antiphronetic states that give rise to the odd parity spin splitting. We understand a little bit about the difference of the energetics in those cases with respect to single band theories, but I think it'd be something interesting to explore.
Okay, thank you.
Okay, and the last question, Jairo.
It's a great talk, by the way. Daniel was always very clear in your talks. I love them. And also, I understand these quasi symmetries. But in regarding the odd parity, and I think it may be a little answer to the previous comment that in polarized conservability, you have to be metallic, and many of the systems, in fact, are insulating. So, particularly the charged ones, the charge density waves part. So, when you talk about this competing with nematicity, we were identifying, like you probably also identified, that in some of the magnetic systems, the magnetic order is actually giving you this strong anisotropy, conducting anisotropy that also can be observed in pneumatic systems, charged pneumatic systems, and connected to the magnetic order. Is that what you're saying, that there could be a competition of those?
Yeah.
I wasn't sure what that meant in there.
Yeah. So when we did the general Ginzburg-Landau analysis, we found 3 different ground states. And those ground states did break up into ferroelectric-like, pneumatic-like, and also this S1 cross S2, or this spin, this odd parity magnet. Now, so I meant in that sense, they're different, but you're absolutely right. In also the odd parity case, the odd parity magnet, we also can have pneumatic order, like you have already pointed out in your work. And so, but
of course, there would be also in the charged ones from that. That may not be a single trigger of it, but I think the Edelstein effect may be something, because it's more magnetic with those symmetries that could actually give you more of a signal to identify one versus the other. Yeah.
Yeah, that's an excellent point. Yeah. But I'm saying, when I say pneumatic, I mean, we don't have any odd parity spin splitting in the pneumatic state, but there's still a spin ordered state that gives us that pneumaticity.
Okay, excellent. Thank you.
Okay, let's go for the next talk. And thank you again, Daniel, for this very nice talk.
Thank you.